We are done with the equivalence of FA and RG from the previous topic. I hope you people remember these sums, wherein first from the RG we have found the FA, and then from FA we have constructed regular grammar. Now the next topic is context-free grammar. If you remember the Chomsky hierarchy, we have 4 classes. The basis for classification is the format of production rules and the related constraints. Then one of the grammar, type 3, regular grammar we have seen in previous 2-3 lectures. Next is context-free grammar. So herein we will be covering these subtopics, which covers the definition, sentential forms, what is leftmost derivation, what is rightmost derivation, parse tree, what is ambiguity, how you will be simplifying the CFG, what are the normal forms related to context-free grammar, Chomsky normal form, Gribach normal form, and of course the pumping lemma. Now, when you consider this RG, which is type 3 grammar, we have said that the language can be represented using regular grammar, finite automata, or regular expression. Then we have seen the concept of pumping lemma. This is repetition, this is theorem, to prove that a certain language is not regular. It's a non-regular language. The example we have, one of the example can be this. We have seen this, that a raised to n, b raised to n, wherein n is greater than 0 is non-regular. And what is the reason this being the non-regular? Because here you need to remember how many a's are there, and then exactly same number of b's needs to be repeated. But as RL is the language of FA and FA does not have memory, so it cannot remember how many times A is repeated. If it cannot remember how many times A is repeated, it won't be able to repeat B exactly the same number of times. And this also means that FA cannot be drawn for A raised to n and B raised to n. As FA cannot be drawn, it is a non-regular language. To represent regular language, you have FA as well as regular expression as well as regular grammar. But in such cases, when the language is non-regular, you require a type of grammar which is called as context-free grammar. And that's why you have type 2 grammar as CFG. Or this is the reason why the concept of CFG exists. Take a minute, go through it. Why there is a requirement of CFG? Because regular grammar, FA, RE and RL, they are related. But if a certain language is non-regular, then what? How to represent it? And for that reason you have context-free grammar. As per the Chomsky hierarchy, it is type 2 grammar. Type 3 we have seen regular grammar, type 2 is CFG. Now generally using the grammar, what you do? Language is represented using set of equations. These equations will be recursive in nature. What these equations will have? Variables, V or non-terminals. Small case letters which are called as terminals. Ultimately, each and every non-terminal will get replaced by terminal. It will form the string or word belonging to the language. And then how you form that word using the production rules represented by capital P, set of production rules. So NTPS or VTPS is nothing but the grammar. Now if you continue with same example, that this is a non-regular language, so CFG is required to represent it. How you will get the CFG for this example? In general, the CFG uses the equations which are recursive in nature. So whenever recursion is involved, infinite looping is also there. And to avoid infinite looping, what you do? You use the base or termination condition. This concept you are familiar from programming languages. So here, for this example, a raised to n, b raised to n, AB will act as the base or termination condition. If you read it carefully, value of n is greater than 0. Greater than 0 means minimum value will be 1. So if you put 1 here, it will give you AB. So that will act as your base or termination condition. Now this a raised to n, b raised to n can also be expressed as a, what remains is a raised to n minus 1, and then this b, what remains is b raised to n minus 1. So in bracket we have clubbed together a raised to n minus 1, b raised to n minus 1, outside this is in concatenation a, in concatenation b. Same thing can be expressed in form of expressions likewise, which are constituting the production rules. What we will say, there is some start symbol. Now this seems to be recursion. N is expressed in form of n minus 1 into 1. A raised to n can be written as a into a raised to n minus 1. B raised to n can be written as b raised to n minus 1 into b, concatenation. So we say start symbol has the base or terminating condition as AB, or it can be recursively written as, this vertical line means or, recursively written as A, S, B. S is calling itself. S is replaced by itself. So when you replace this S by ASB, it will be likewise. This yellow highlighted S is been replaced by one of its alternative value, which is ASB. And then this S, which is now highlighted in green, is been replaced by AB, which is another alternative value for the replacement of S. And that's why we got previous double A, then AB, previous double B. So by this way we have generated A cube, B cube. A is appearing 3 times, B is appearing 3 times. So when you write this in grammar ka format, that is collection of NTPS, this will be your set of production rules. S is itself start symbol. How many terminals you got? Small a, small b. How many non-terminals or capital case letters are there? Only one, capital S. So this will be now your CFG. Collection of this will be CFG, which is type 2 grammar. context-free grammar. I hope this is understood. We have started with the example of non-regular language. To represent regular language, you have FA, you have regular grammar, you have regular expression. Now, if the language is non-regular, what to use? FA cannot be used. So, type 2 grammar, context-free grammar is used. Again, we proceeded with the same example. Here, in CFG, you will find set of equations which are recursive in nature, and those equations will constitute capital case letters which are called as variables or non-terminals, and small case letters which are called as terminals. So for this same example, you have tried to express a raised to n, b raised to n as likewise in the form of recursion, which will obviously have some base or termination condition. And this is what you have derived CFG for same example, which is non-regular. So this is the required CFG. Now comes the definition of CFG. It will be same as that of start will be same as that of generalized definition of grammar. So you say that CFG is quadruple NTPS, where N you are supposed to write 4 lines, 1 line per tuple. N is the finite set of non-terminals, T is the finite set of terminals, P is the finite set of production rules, S is the start symbol. And then you come to the constraint part, which is explaining what is the format of each and every production rule of CFG. So next line says that production rule is of the form A can be replaced by alpha, where A is a non-terminal, so it is said to belong to capital N, whereas alpha belongs to T union N star. T union N star is nothing but a, I hope you people remember, sentential form. Union of terminals and non-terminals and its combination. So, in descriptive format, how you will represent this restriction on the format of production rule? In this grammar, restriction on production rule is that LHS should contain only one non-terminal symbol. So that's why there is capital A which belongs to capital N. There is no restriction on RHS side. It is simply a sentential form. It may be single or multiple terminal. It may be single or multiple non-terminal. It may be combination of both in any sequence. But LHS should have only one non-terminal. So this is regarding the formal definition of CFG, context-free grammar. Same example we continued with a language of the form number of A's followed by exact same number of B's, where n is greater than 0. In descriptive format, this can also be expressed as in general. Likewise, L of G is a language which is collection of all W's such that W is what? Generalized name for representing a string or word such that W belongs to T star. T is what? Set of terminal symbols, collection of small case letters only. When it is said star, multiple combinations or looping will be there. This whole expression means you start with the start symbol S. This means multiple. This is production rule. By applying production rules multiple times, you derive W, which belongs to this language. So you say that L of G is the language defined by grammar G, which is the collection of all the words such that this word consists of all terminal symbols only, and this word can be derived from the start symbol by multiple applications of production rules. Same thing is written here. So this expression will be called as derivation of string from the start symbol S. Take a minute, go through this. Now this derivation can be represented in two ways. This derivation, wherein you start with the start symbol capital S, apply multiple production rules and try to derive a valid word or string belonging to the language. So these derivations are represented either using sentential forms or parse tree form. Sentential forms again can be divided into left sentential form or left derivation, rightmost derivation, right sentential form. How it works? Consider the example wherein the grammar is given likewise NTPS with the value of NTPS likewise. S is the start symbol. From S, you are supposed to derive this W, which is 00101. How to derive a string? This is the expression. So, we have written the start symbol, expansion of the leftmost symbol, and which production rule is used for this. The very first, this production rule we are using here. Now, sentential form can be of subtype leftmost derivation. So in that case, what we are doing, we are selecting the leftmost non-terminal symbol for expansion. So we are in the next step going to expand A, because the ultimate aim is that it should contain only terminal symbols. Which are the terminal symbols here? 0 and 1. Right now, as per the equation, LHS side consists of non-terminals capital A, capital B. So you need to replace their values in such a way that you will get 00101, as the subtype is leftmost derivation. You expand leftmost symbol. So highlight this. What are the possibility of replacing A? There are two possibilities of replacing A. A can be replaced by 0A or epsilon. You want 0 to be the leftmost symbol, so you are considering 0A as the replacement of A, and that's why in the next step you will find that A is expanded as 0A, this 1B is kept as it is. Which rule is applied? A is replaced by 0A. And likewise, the way you solve the mathematical expressions, equations by replacing the values of variables and ultimately find the solution which is variable free and has a numeric value, maybe integer, maybe decimal. Likewise, you need to replace these to find a string containing terminal symbols only. Again, you highlight the leftmost symbol, which again turns out to be capital A for the replacement. You want 00 before 1, so we are replacing again this A by 0A. This 0 is kept as it is. This 1B is kept as it is. Again, the production rule which is applied is A is being replaced by 0A. Before this 1, you want 00. But in between 00 and 1, you got A. Whether it is required? No. Can you eliminate? Yes, by putting epsilon for this A. And that's why, this being the leftmost symbol, in the next step, you will find that this A is being replaced by epsilon. By applying the production rule, A can be replaced by epsilon. So you got 00 epsilon 1 B. This can be ignored. So ultimately you got 001 B with you. 001 is obtained. What else is remaining? You want B to be replaced in such a way that 01 should appear. So your next target, leftmost symbol, again happens to be B, which will be now replaced by, here you are ignoring this epsilon. After ignoring epsilon, you got 001B. B is highlighted to be replaced. What are the possibilities of replacing B? Three possibilities are there. 0B, 1B, epsilon. What you want after this one? 0. So you will choose B to be replaced by 0B. Highlight B, that's the one you are replacing. Apply replacement by 0B. And again highlight this B, because this will be now replaced in the next step. What you want after this 0? 1 to appear. Do you have any such possible replacement? Yes, B can be replaced by 1B. Next step में you will find the same. B is replaced by 1B. So after this one, 0, 1 and B is appearing. Select this B. This is now the leftmost. This is the only and will be leftmost or rightmost symbol to be replaced. We are going leftmost way, so we consider this to be leftmost. That's the only non-terminal to be replaced. Get it eliminated by putting epsilon for that. So in the next step, again replace epsilon for that, and then simply ignore it. You got 00101. So here the non-terminal symbol appearing on the leftmost side of RHS is selected for the replacement every time. So this is called as left sentential derivation form or leftmost derivation. Take a minute, go through this. Aim is to derive 00101 from S. Similarly, instead of starting with this A, if you start with B, B being the rightmost symbol for replacement. So now you will find it. Rightmost derivation. Choose the rightmost symbol for replacement every time. Now, after on the right side of this one, what you want? 0, 1. So after this 1, 0 should be there. After this 0, 1 should be there. So which alternative amongst these three you will be going for? Replacement of B should be with 0B and then with 1B and then epsilon. Same thing we have done in these three. B is first replaced with 0B. 10B you got. Again this B is replaced with 1B. Ultimately B is eliminated by putting epsilon. So out of these two, every time you chose rightmost NT non-terminal for the replacement. Now you are left with only one non-terminal on the RHS side. So that will be now considered as the rightmost non-terminal or variable available for the replacement. On the left of this middle one, what you want? 00. A is the non-terminal. Two possibilities are there for the replacement. So twice you will be replacing it with 01 and D. For the last time A will be eliminated by putting epsilon for it. So A is highlighted. Twice it is been replaced with 01. So here for the last time you are replacing it with epsilon and then ignoring that epsilon. You got 00101. So this will be the rightmost derivation, as the rightmost symbol is selected every time for replacement. Which symbol? Non-terminal symbol or capital case letter. Take a minute, go through this. Column headings are start symbol, expansion of rightmost symbol, production rule applied for the expansion. Now from the same example, second word is 1001. You proceed with S to be replaced by A1, B. You go leftmost derivation way. So A is highlighted to be replaced. This A is been replaced with epsilon in the very first go. So a non-terminal is been eliminated by replacing it with epsilon. You are left with 1b. B is the only symbol, so it will act as leftmost symbol and that will be replaced every time. You want 1 के बाद 00 and then 1. Possibilities are replace it twice with 0b, then by 1b and finally by epsilon. And that's what you will find here. B is replaced with 0b. Again 10 stays as it is. Highlighted B is been replaced by 0b. And lastly, replace it with epsilon. 1b epsilon. So you got derivation of 1001. Take a minute, go through it. This is leftmost derivation. Same word with rightmost derivation. You start with replacement of start symbol by A1B. As this is rightmost symbol, a rightmost derivation, rightmost symbol is selected, which is B now. It will be replaced with same thing, 0000 twice and then by 10. Finally, B is replaced with epsilon and A will also be replaced with epsilon. So now let us bring this both the tables in the same screen and notice the difference. It's not exactly reverse, right? ये टॉप डाउन ये बॉटम अप है ऐसा नहीं है. The sequence of applying production rules, they are not exactly reverse of each other. They are changing. Same as that of replacing variables in mathematical equations. So I hope this is understood. This is the generalized form expression which is called as derivation of string from the start symbol S. By repeated application of production rules, you get W, valid string belonging to a language. We are done with sentential forms. The second way is parse tree. These ways are there for representing derivations. Sentential forms में just now we have seen leftmost derivation, rightmost derivation. This parse tree, as the name suggests, is the pictorial way of representing derivations. Tree structure is used to represent the applied production rules, and that tree structure is nothing but a parse tree. What rules are applied to construct this parse tree? The root is represented by the start symbol because you are starting with capital S every time for any of the W. Each internal node is represented by non-terminal or capital case letter. The root is capital S, which is also a non-terminal. Internal nodes are also capital case letters, non-terminals. Only the leaf nodes are represented by terminal symbols, small case letters. So as the derivation is obtained either by replacing the leftmost symbol or rightmost symbol, parse tree can also be built in two ways. How you will derive the string or write the string from the given parse tree? Use in order way of parsing or traversing it. In order way will be left, root, right. So basically you are traversing the tree from left to right direction. We have continued with second example wherein we are deriving 1001 leftmost derivation and rightmost derivation. Just now we have seen it above. Using these derivations you are drawing this parse tree. So you started with this root node represented by S. If you consider leftmost derivation, first you will have S expanded as A1B, and out of this A and B as non-terminals, leftmost A is selected for the replacement of epsilon. So you will find that this branch will be expanded by connecting epsilon, which belongs to terminal symbol, to this non-terminal A, and you will find that this is a leaf node. 1 is already a non-terminal terminal symbol, so that is not expanded. The only symbol you are left, variable or non-terminal, for expansion is B. 1 is already there. After that you want 001. So this B is twice replaced by or expanded likewise 0B. Again attach 0B. Ultimately replace this B by 1B and B is replaced by epsilon. So first you started with a root S. This S is expanded by A1B. So you got this second layer. Out of this A and B, you select leftmost symbol for expansion. A is to be replaced by epsilon. So this branch is expanded first. Epsilon being the terminal symbol, no expansion is possible. Next you find there is 1 which is already a terminal symbol, no expansion is possible. Only non-terminal is B. Expand it first by using 0B, again 0B, 1B, ultimately epsilon. How to read this now? Left to right in order fashion. So you will write left, root, right, epsilon, 1, 0. You won't write this is non-terminal. Then comes here 0 के बाद again 0. You won't write this. You will come here 1. You won't write this. You will come here. You will write epsilon. Only terminal symbols to be written. So for this upper half of the table, you got this parse tree. Similarly, for rightmost symbol, every time for the 1, 2, 3, 4, you got 4 B's expanded. So first You start with this S, replace it with A1B, and you go this way for the expansion. 0B, 0B, 1B, epsilon. And then this branch will be expanded. Now, once you found these both the pass trees, there will be a concept called as ambiguity in PFG. So, if the left derivation pass tree and the right derivation pass tree, they are both different, even for a single word, or you can say at least for a single word in the grammar or the language, the grammar is called as ambiguous grammar. Take a minute, go through this. There can be multiple, either finite or infinite words in the language. Consider that there are 15 words. For the 14 words, you are getting left derivation pass tree and right derivation pass tree same. But even if for a single word, or at least for a word, if it is not equal, then such a grammar is called as ambiguous grammar. And this ambiguity is not at all the desirable character. Both the pass trees are now appearing in the same screen. You can check them out. You will find that for this 1001, left derivation and right derivation, they are same. So you say that given grammar is non-ambiguous grammar. Consider this next example, wherein the grammar is given as E can be replaced with E plus E or A or B. And you are supposed to draw the pass tree for W, which is equal to A plus B plus A. Now two ways are possible to derive A plus B plus A. First you find A plus B and then add A to it, or first you go from the right, you find B plus A and then add this first A to it. So if you derive in this way, what you need to do? You will start with E is equal to E plus E. So you got E as the root node, which is expanded as E plus E. Next, ये वाला tree is first drawn. Next, consider this one highlighted with the green. As you want B plus A to be evaluated first, bracket will have higher priority. So we are expanding this rightmost symbol E again by E plus E, and this E's non-terminals are ultimately replaced by B and A. So you got B plus A here, and then this E is expanded as A. So here A plus B plus A you got likewise. And if you want to go this way, जो highlighted नहीं है, A plus B and then plus A. So here you will find that A plus B is expanded likewise. Leftmost E is selected for the expansion. It's been replaced by E plus E, ultimately by terminals A and B. So this bracket got calculated A plus B, and then A is added here. We are bringing both the trees in one screen. This one is for A plus in bracket B plus A. This one is for in bracket A plus B plus A. So you find that they are different. So you say that ambiguity is there. And this ambiguity is not at all a desirable feature. So this is the URL wherein you need to explore this concept more. And let me share the next PDF, which next Word file, wherein we will see how we will remove this ambiguity. Even in math, to avoid such kind of situations, what you do, the precedence is given I hope now the next Word file is visible, which says past tree and ambiguity in grammar, lecture board 3. So we will continue with how we will remove the ambiguity. I'll again display that Get Vidyalaya URL, wherein you will explore more examples. So a grammar is ambiguous. You say a grammar is ambiguous when language generated by the grammar contains some string or at least one word that has two different past trees. Now two different past trees may be related to two different left derivations or might be related to two different right derivations. Generally, the left and right derivation tree will be different. So as ambiguity is not desirable feature, you need to remove it because certainty is not there that for this kind of input exactly this output will be achieved. So as such, you don't have any algorithm or technique or steps to remove ambiguity. You simply need to rewrite the grammar so that there is only one derivation tree possible for every string belonging to the language. Every string belonging to the language means obviously a valid word. So remember, no rules or algo or technique is there to remove the ambiguity. You simply try and rewrite the grammar so that now only one way will exist. If you remember the previous example of A plus B plus A, two ways are possible, and that's because of associativity, if you can relate with the rules of mathematics. So deriving A plus B and adding later on A to it is same as that of first adding B plus A and later on adding A to it. So you don't allow these possibilities. So let us try to rewrite this same grammar. So in this is the question which you will find in every university paper. Check whether the ambiguity exists in the grammar. If at all it is, remove it. So we have started with the stepwise solution wherein we are saying that check the given grammar is ambiguous or not. So we have taken the W ka value won't be given in the exam. W ka value you need to decide on your own, and by experience and practice only you can find out that For particular example, this will be the value of W, which will have two different parse trees. So now this example we are repeating third time. So if this same example comes, by now you know that A plus B plus A is the value of W, for which two possible derivations are there, related two different parse trees are there, and by this you can show that this is ambiguous grammar. It is not required. Ambiguity is not required, so then you will proceed. So same thing is given here, related parse trees. So ambiguity is there, as two different parse trees are possible. To remove the ambiguity, rewrite this grammar. So how you are rewriting it? Ambiguity can be removed by strictly assigning the higher precedence to left side plus operator over right side plus operator. So you are rewriting the grammar in such a way that you will be evaluating this expression from left to right. So you have decided that you will be evaluating it likewise only. So higher precedence is given to left side plus. So it's A plus B are added first and then to the right wala plus. So how this is possible, how this can be achieved? By introducing one more variable T in the given grammar. So in general, if you relate this with maths, you will find that E stands for expression, T stands for term. Right now E ka possible values for replacement are E plus E, A or B. So what you are doing, you are making this E, left wala E, possible for expansion. So as it is possible to expand it, LHS and RHS ka E is same and then plus T, this term. Initially it was E can be replaced by E plus E. Now you will find it as E can be replaced by E plus T or T, and T is taking value of AB. Initially E was taking all three values. So if you can visualize this in the tree wala diagram, E will be at root, this will be left child, rightmost child, in between plus, and then possibility of expansion E is there, which will be again expanded as E plus T, and then E will be replaced by T. Ultimately T takes value A. So A plus B first evaluated and then this A is added. We'll continue with this example in the next lecture. Let me share the attendance link.